I'll show the results of the drop test here. So we've got the 25 mass, which is 650 grams, dropping from a height of 4 centimetres, which is the one height. And then we've got the 1 mass, which is 26 grams, falling from a height of 25 times that, so 100 centimetres, to measure the energy. In the previous video, I showed the uncompressed length of the spring. That was 103.3 millimeters. I then put the 25 mass on. We've got a remainder of 98.6. So we take that from that. So the 25 mass, or the 650 gram mass, under its own weight, compressed the spring 4.7 millimeters. So when we drop it, obviously it'll compress the spring plus its weight, so we've got to eliminate this. So when we drop the 1 mass, we can get a rough idea of what we should see compression wise. Also, I'll try and verify the velocities as best I can. I've taken a crop, but even in slow-mo it's actually still quite fast, so I'll probably slow that video down. I think when I looked at it, it was like 4 seconds for the 25 mass and 0.8 seconds for the 1 mass at 5 velocity. But it happens that quick. I'll like slow. It's the same frame rate, obviously. It's about 2,000 frames a second, so I'll slow that down by the same rate again, so it's easier to see. But obviously on the two raw footage, you know, people can analyse that to see if it is going at exactly 5 the velocity, but you know, from the heights alone, should be thereabouts. I'm a bit pressed for time at the moment, so I'll just show one drop of each in its raw form, then I'll zoom in and edit. You know, well, yeah, just not really editing, just putting markers on so we can see roughly the compressions. So just seeing the 25 mass fall in there, rough compression of 22 millimeter. Obviously we've got this weight factor, so when we drop the 1 mass from 25 times the height, we should see roughly around this mark, about around the 17 mil mark, maybe a bit more, a bit less. Like I say, to say, you know, I'm doing it exactly and precisely, clearly I'm doing it the best I can, and like I say, it's a very good indication. So on with the show, we'll see what that does, eh? So as we can see there from the 1 mass falling at 5 velocity, 5 times the time, we're getting a rough compression around this mark, around the 17 millimeter mark, which is what would be predicted for the energy. Again, not super precise, working with new apparatus. When I've got more time, I'll probably do it again, spend a bit more time doing it. It's been a bit of a rush job, but it's, you know, it's thereabouts. So the MGH formula and the kinetic energy formula roughly predict the results. I don't know, you know, in terms of momentum, we didn't, you know, I don't know what the prediction would be for that. But we didn't get one, did we? We didn't get a prediction. But obviously the energy formulas perfectly, or almost perfectly, predict the results. So this is both drops overlapped. The one mass drops in, the marker goes, so the upper edge of that white line is the maximum compression of the one mass, and then the 25 mass drops in, and again the upper edge of the marker on that one, so the shaded area in white is the difference in compression, which I'd say is around about 5 mil difference, which is the weight compression. Also, just to add here, both images are overlapped, so if we look at the numbers, obviously if there's any out of alignment, you'd see some ghosting on the numbers, so it just shows that they were taken from exactly the same perspective. So what I've just shown, you know, the measurement wise, is very accurate in that respect, because they are taken from the same perspective. So thanks for watching, everyone. It's another interesting one.